Chapter 2. Outline of Electromagnetic Connections. 20. Our primary knowledge of electricity, in its quantitative aspect, is founded upon the observation of the mechanical forces experienced by an electrically charged body, by a magnetized body, and by a body supporting electric current. In the study of these mechanical forces, we are led to the more abstract ideas of electric force and magnetic force, apart from electrification, or magnetization, or electric current to work upon and produce visible effects. The conception of fields of force naturally follows, with the mapping out of space by means of lines or tubes of force definitely distributed. A further and very important step is the recognition that the two vectors, electric force and magnetic force, represent, or are capable of measuring, the actual physical state of the medium concerned. From the electromagnetic point of view, when taken in conjunction with other quantities experimentally recognizable as properties of matter, showing that different substances are affected to different extents by the same intensity of electrico or magnetic force. Electric force is then to be conceived as producing or being invariably associated with a flux, the electric displacement. And similarly magnetic force as producing a second flux, the magnetic induction. If E be the electric force at any point, and D the displacement, we have D equals C times E. And similarly, if H be the magnetic force and B the induction, then induction, B, equals permeability or inductivity, mu, times magnetic force, H times H. Here the ratios C and mu represent physical properties of the medium. The one mu, which indicates capacity for supporting magnetic induction, is its inductivity, whilst the other, indicating the capacity for permitting electric displacement, is its permittivity. Otherwise, we may write electric force, E, equals displacement flux, D, over permittivity C. Magnetic force, H, equals induction, B, over permeability or inductivity mu. And now the ratio 1 over C is the elastivity and 1 over mu is the reluctivity or reluctancy. Sometimes one way is preferable, sometimes the other. Electric and magnetic energy. 21. All space must be conceived to be filled with a medium which can support displacement and induction. In the former aspect only it is a dielectric. It is, however, equally necessary to consider the magnetic side of the matter, and we may, without coining a new word, generally understand by a dielectric a medium which supports both the fluxes mentioned. Away from matter the medium concerned is the ether, and mu and c are absolute constants. The presence of matter, to a first approximation, merely alters the value of these constants. The permittivity is always increased, so far as is known. On the other hand, the inductivity may be either increased or reduced, there being a very small increase or decrease in most substances, but a very large increase in a few. The so-called magnetic metals. The range within which the proportionality of flux to force obtains is then a limited one, which, however, contains some important practical applications. When the fluxes vary, their rates of increase .B and .D are the velocities corresponding to the forces E and H, provided no other effects are produced. The activity of E is E.D, and that of H is H.B. The work spent in producing the fluxes is, therefore, U equals integral between 0 and D of E dd, and T equals integral H dB. Where U is the electric and T the magnetic energy per unit volume. When mu and c are constants, these give U equals half Ed equals half c squared, and T equals half Hb equals half mu h squared. To express the energy stored in the medium, electric and magnetic respectively. When mu and c are not constants, the previous expressions in equation 5 will give definite values to the energy provided there be a definite relation between a force and a flux. If, however, there be no definite relation, the energy stored will not be strictly expressible in terms simply of the force and the flux, and there will be usually a waste of energy in a cyclical process, as in the case of iron, so closely studied by Ewing. This does not come within the scope of a precise mathematical theory, which must of necessity be a sort of skeleton framework, with which complex details have to be separately adjusted in the most feasible manner that presents itself. Elotropic relations. Note, here, elotropic means having properties with different values along different axes. 22. But a precise theory nevertheless admits of considerable extension from the above, with mu and c regarded as scalar constants. All bodies are strained more or less, and are thereby usually made elotropic, even if they be not naturally elotropic. The force and the flux are not then usually concurrent, or identical in direction. But at any point in an elotropic substance there are always, if force and flux be proportional, three mutually perpendicular axes of concurrence, the principal axis. When we have, referring to displacement, d1 equals c1 e1, and d2 equals c2 e2, and so on. If the c's are the principal permittivities, the e's the corresponding effective components of the electric force, and the d's those of the displacement. If E be parallel to a principal axis, so is D. In general, by compounding the force components, we obtain force, E, the actual force, and by compounding the flux components we obtain D, the displacement, to correspond, which can only concur with E in the above-mentioned special cases if the principal permittivities be all different. But should a pair be equal, then E and D concur in the plane containing the equal permittivities, for the permittivity is the same for any axis in this plane. The energy stored is still half the scalar product of the force and the flux, or half ED, understanding that the scalar product of two vectors, which is the product of their tensors when they concur, is the same multiplied by the cosine of their included angle in the general case. Vector analysis is, I think, most profitably studied in the concrete application to physical questions, for which, indeed, it is specially adapted. Nevertheless, it will be convenient, a little later, to give a short account of the variolemptance of the subject, in order not to have to too frequently interrupt our electromagnetic arguments by mathematical explanations. In the meantime, consider the dielectric medium further. Distinction between absolute and relative permittivity or inductivity. 23. The two quantities C and U are to be regarded as known data, given over all space, usually absolute constants. But when the simpler properties of the ether are complicated by the presence of matter, then varying in value from place to place in isotropic but heterogeneous substances, or, in case of elotropy, the three principal values must be given, as well as the direction of their axes, for every point considered. Keeping to the case of isotropy, the ratio C over C0 and U over mu0 of the permittivity and inductivity of a body to that of the standard ether are the specific inductive capacities, electric and magnetic respectively, and are mere numerics, of course. They do not express physical properties themselves except in the limited sense of telling us how many times as great something is in one case than in another. This is an important point. It is like the difference between density and specific gravity. It is possible to so choose the electric and magnetic units that mu equal 1 and C equals 1 in ether. Then mu and C in all bodies are mere numerics. But although this system used by Hertz has some evident recommendations, I do not think its adoption is desirable, at least at present. I do not see how it is possible for any medium to have less than two physical properties effective in the propagation of waves. If this be admitted, I think it may also be admitted to be desirable to explicitly admit their existence, and symbolize them not as mere numerics, but as physical magnitudes in a wider sense, although their precise interpretation may long remain unknown. If, for example, h be imagined to be the velocity of a substance, then 1/2 mu h squared is its kinetic energy, and mu its density. And if E be a torque, then 1 over c, the elastivity, is the corresponding coefficient of elasticity, the rigidity, or quasi-rigidity, as the case may be, while c is the coefficient of compliance, or the compliancy, and 1/2 c times E squared is the stored energy of the string.